A simple model for travel costs involves the cost of gasoline and the cost of a driver. Specifically, assume that gasoline costs P dollars per gallon and the vehicle gets G miles per gallon. Also assume that the driver earns W dollars per hour. Okay, so our first question, a plausible function to describe how gas mileage in miles per gallon varies with speed is g of v equals v times 95 minus v divided by 70. Evaluate g of 0, g of 40, g of 60, and explain why these values are reasonable. So we're given this formula or this equation function, and it's said that it describes gas mileage based on speed. So as you may or may not know, as you drive different speeds, you're going to get different gas mileage. So if you put the pedal to the metal, so to speak, and go 100 miles an hour, you're not going to get very good gas mileage. But also, if you are barely going down the road at all, you're not going to get very good gas mileage that way either. It's somewhere in the middle. So this equation or this function that we're given says that it's a good representation, and it asks us to verify if it's a good representation. So to verify it, we can just plug in the values that it asks in place of v, because this is a function of v. So for g of 0, we get 0 times 95 minus 0 over 70. Obviously, that's 0. So, I mean, that makes sense. If you're going 0 miles an hour, you're using 0 gas. So that's not really, I mean, that's to be expected, but that didn't really help us too much. Let's move on to g of 40. G of 40, we have, let's see, 40 times 95 minus 40 over 70, and we can type that into the calculator. So 40 times 95 minus 40 divided by 70, and we get that's about equal to 31.43. Okay, so 31.43 miles per gallon. Okay, so that's saying that if you in this particular car, if you drive 40 miles an hour, you're getting 31.43 miles per gallon. That's pretty good. It's pretty good gas mileage. So let's see what happens when we go 60 miles an hour in this car. So 60, give us 60 times 95 minus 60 over 70. Okay, you can just change these numbers to 60. There we go, and you get 30 miles per gallon. Okay, so as you increase your speed up to 40, you get 31.43 miles per gallon. If you increase it up to 60, it drops a bit down to 30. Now, if we were to plug in a much bigger number, I mean, like let's say like 70 or 80, we could try that. It didn't ask us to, but we can, just to see if it keeps dropping, and it looks like it does. Okay, so it keeps dropping up to a certain point, and you have to assume a little bit in this problem that as you increase your speed up and up and up to 90, 100, 120 miles an hour, that your gas mileage is going to continue to decrease. So at some point this model may break down, and you just have to use your common sense on that. But this does look like a plausible function. Okay, so let's move on to B. It says at what speed does the, sorry, a little typo there, does the gas mileage function have its maximum? Okay, so if we're given the function for gas mileage and we want to find its maximum, well, we need to take the derivative. Okay, so if we're given that g of v is equal to v times 95 minus v over 70, I'm going to even distribute that a little. I'm going to say 95v minus v squared over 70. Okay, and you could even split that up if you wanted, 95v over 70 minus v squared over 70, and do it term by term. So g prime of v, the derivative of this function, is going to be 95 over 70. That's the first term. And then the second term, remember you bring the 2 down, so it becomes negative 2v over 70, and then you could just put that back together again. 95 minus 2v over 70 is your derivative, which will help us find our maximum. Okay, so when we're going to find the maximum, we need to set this thing equal to 0 and solve. So we'll set this thing equal to 0, and let's see, we get 95, I'll just do it over here, 95 minus 2v over 70 equals 0. The 70 is going to immediately cancel when we multiply it over, so it's just 95 minus 2v equals 0. So negative 2v equals negative 95, and v is equal to 47.5. Okay, so that's where for this function, that's where your maximum gallons is going to occur. Now, how do we know that's a maximum and not a minimum on that critical number? Where you can look at the function itself and say, okay, well, this is the function. It's got a negative v squared, right? Think of it in terms of negative x squared. That's an upside down parabola. I mean, it looks like that, right? So we know that that's going to be a maximum. Okay, so this v is equal to 47.5 gives you the exact place where you get the absolute best gas mileage. Okay, let's move on. Okay, this one is going to be, let me get a new paper here. This one is going to take some doing, especially the next one. Okay, so it says explain why C, this is a cost function, equals LP over G of V plus LW over V gives the cost of the trip, where dollars, or in dollars, where L is the length of the trip and V is the constant speed. Okay, so some of this stuff we were given earlier. So if we have C of V equals LP over G of V plus LW over V. Okay, so let's stop and think about, okay, the length is in terms of miles, right? So if I wrote this out in just its units instead of writing the variables, I'll just write the units. So the L I would put, that's miles. Okay, and then the P, let's see, that was given in the beginning of the problem. Up here, it said that is money per gallon, dollars per gallon. Okay, so I'll put money per gallon on that. Okay, and then at the bottom we have the G of V function, which we already know is miles per gallon. Okay, so when you look at this, we have miles on top and miles on bottom, those cancel, and then per gallon on top and per gallon on bottom also cancels. That's money. Money is all that's left there. That's the first term. I didn't do the second term yet, but that's the first term. That's the LP over G of V. We can do the same thing for the LW plus V. So that would be, L is again miles. Okay, and then W, it says, is money per hour. So money per hour. And then on bottom we have V, which is miles per hour. That's velocity. Miles per hour. And just like over here, we've got miles and miles, they cancel. Per hour cancels, and you're left with money. So once everything cancels out, you're left with just money. And that makes sense because this is a what kind of function? Cost function. Okay, cost, money. Done. Okay, for letter D, it says let L equal 400 miles, P equals $4 per gallon, W equals $20 an hour. At what constant speed should the wow, I really bungled that word, didn't I? Okay, so that should have said vehicle. So what let's see. Yeah. Okay, so vehicle be driven to minimize the cost of the trip. So we're going to take this function, C of V, and this is going to take some work. So stick with me on this. Okay, so we'll take the C of V function here. Okay, and let's see, the first thing that we want to do is, since we are minimizing, we want to take the derivative with respect to v. So before we can take the derivative, we can't have a function within a function, right? So we need to go back to where we had this function g of v lined up here, and that was v 95 minus v over 70. So I'll plug that one in right here in place of g of v. So I get c of v equals LP over V times 95 minus V over 70. plus LW over V. Okay, so let's clean that up just a bit before we go ahead and take that derivative. The 70 can go to the top. You get 70 LP over, let's go ahead and distribute that so we can take the derivative more easily. So it'd be 95V minus V squared. We might undistribute that later. I'm not sure. We'll see. And plus LW over V. Okay, so the derivative of this cost function. The derivative of the cost function, remember, we're only taking the derivative with respect to V. Okay, so the derivative of this cost function, we're looking at this function here. This is quotient rule. Both of these are really quotient rules there. Okay, so quotient rule here says you take the derivative of the top times the bottom. Okay, the derivative of the top is 0, so that's going to be 0 times 95 V minus V squared minus the derivative of the bottom times the top, which is, let's put the 70 LP out front. That's the top, and then the derivative of the bottom is 95 minus 2V. Okay, and that is over the bottom squared. I'm going to undistribute that and then square the whole thing. Okay, and then of course we've got this one, which if you write this as LW V to the negative 1, then you bring down the negative 1, so that makes the whole thing negative, and you make it a negative 2 and bring it back to the bottom. So you get minus LW over V squared. Okay, so obviously the 0 term cancels out. Okay, so we get negative 70 LP times 95 minus 2V over V squared, and then 95 minus V, quantity squared, minus LW over V squared. Okay, so that's kind of cleaned up for us. It's still got a lot of variables in there, and you're probably wondering why you're not just going ahead and plugging in the numbers, the you know, the 20 and the 4 and all those things. Well, I tried it that way. I actually worked through the problem that way, and the numbers got so huge that I felt it was better to just leave in the variables. Well, they're not really variables, but leave in the letters in place of the numbers for now, and then when we start solving the problem at the end, we'll plug in those values. Okay, so we're going to set this equal to 0 and solve. Okay, so the first thing I want to do is get rid of the V squared. Both terms have a V squared, so if I multiply all 3 times V squared, that one's gone. Okay, so cancel, cancel. So we get 0 is equal to negative 70 LP times 95 minus 2V over 95 minus V, quantity squared, minus LW. Okay, and then we can, let's see, we can move this term over to the other side and make it positive. So LW is equal to negative 70 LP times 95 minus 2V over 95 minus V, quantity squared. We can multiply that term over. So I get LW times 95 minus V squared equals negative 70 LP times 95 minus 2V. Okay. The next thing we can do is both sides have an L in them. So instead of plugging in that L, which was a big number, what was it? It said L was equal to 400. You probably didn't see that. I did that too fast. L was equal to 400 right there. But we get to cancel L out. So we get to not put the 400 in there, which makes the numbers significantly smaller when you get rid of that 400. So you get W times 95 minus V, quantity squared, equals negative 70 P times 95 minus 2V. So it's starting to look a little better, and I'm also starting to run out of paper. So let me keep going on another sheet here. This is a big problem. Okay, so let's see. what to do next? Well, we need to square this term out, and then we also need to distribute this. So let's do that both in the next step. We'll keep the w out front over here. Square that term out. That gives us 95 squared minus two of the middle terms with the v times the 95. Okay. There's a reason why I'm keeping it this way. You're probably wondering why I didn't just put, 190. But you'll see. And then plus v squared. And then that's equal to negative 70p times 95 minus 70p, or it's plus 70p times 2v. Okay, so that gives us, let's see, w times 95 squared minus 2v times 95w plus w v squared. And then the other side, I might put the 2v out front of the 70p. That's everything else I'm going to leave the same. Negative 70p times 95 plus 2v times 70p. Okay. I want to get rid of that w in front of the squared term. So I am going to divide every one of these by w, which means I have to do it on the other side as well. Okay, so that will give us 95 squared minus 2v times 95 plus v squared equals negative 70p over w times 95 plus 2v times 70p over w. Okay, again, I'm keeping these numbers like this for a reason, so stick with me on this. Okay, I want to combine everything to the same side, so I can move everything, I can move these two terms over here. And let's write it in order because this is going to be a quadratic. So let's write the v squared first. Okay, and then my next term is going to be the v term. So I've got this one. I've got the minus 2v times 95. And when I move this term over, it becomes a minus as well. So also a minus 2v times 70p over w. And then I've got the 95 times the 95, which is the 95 squared. Let's write it as 95 times 95. And then this term comes over. It's negative, but when I put it over the other side, it becomes positive. So plus 70p over w times 95 equals 0. Now we've got like terms. We've got a couple of negative 2v's here with this, so we can factor the 2v out, or the negative 2v out. We also got the 95's here that can be factored out, and this stays on the inside. So we get v squared minus 2v 95 plus 70p over w. That's these two terms. That's the inside. So we factored out the negative 2v that left the inside. And then we'll do the same thing here. We'll factor out the 95. And then on the inside, we get a 95 plus 70p over w equals 0. Okay, that was a lot of work. What did it accomplish for us? Well, it accomplished that we have a quadratic that we can solve. Okay, and we can actually now put the numbers in. Now that we've got it kind of simplified, we can put these numbers in and get actual numbers for this. Remember that L equals 400, but we don't have any more L's. P equals 4, W equals 20. So V squared minus 2V times 95 plus 70, P equals 4. So 4 over W equals 20. And then the same thing for this one, 95 plus 70 times 4 over 20 equals 0. Okay, if you multiply that all out and get and work that all out, you're going to get V squared minus 218V plus 10,355 equals 0. Okay, so you've got to solve this quadratic to get our critical numbers here. So you can solve this with the quadratic formula. You can solve this by typing it in your calculator and looking at the graph and finding the 0. Either way works. we've done a lot of work already. Let's go to the calculator. Okay, so I've typed it in already for us. So we have x squared minus 218 plus 10,355. And I'll show you my window here, 0 to 200. And then the y min, y max probably doesn't need to be that big. I think 100 will be more than enough for those. Okay, let's take a look at the graph. Okay, there's the two places that it crosses. Now, remember, this is a parabola. This time a right side up parabola, not like the original function. So second, calculate 0. And let's see, where is my... This thing seems to be going down as I go left, so it's coming from this direction. And okay, let's try this another way. Instead, I'm going to type in 0, and that's going to give me a line here you can't see. And now I can hit second trace and just do an intersection. Enter, enter, enter should give me the first intersection, so that is fine. So that gives me v is equal to, and this is approximate, but we're going to say 69.9. And then let's find the other intersection. It's going to be over here. It's going to take me a second. Okay, so that should be good enough. And that one gives me v is equal to 148.1. Okay, so in terms of the original question and what we think these two answers means, let's go back to the original question, and it says, at what constant speed should the the vehicle be driven to minimize the cost of the trip? Okay, so at what constant speed to minimize the cost of the trip? So should it be driven around 69.9 miles an hour, or should it be driven at 148 miles an hour? Well, the answer to that should be pretty obvious using just your common sense. But why is it that one is chosen over another? Well, you'd have to pay attention to the original graph, and the original graph was parabolic, and it let's see, it no longer it had a asymptote on it, the original function. Trying to go back and find, I've got a lot of papers here. I had the original function here. So the original function for the cost function had a v times 95 minus v in the denominator. Okay, right here. Okay, which created an asymptote. We had an asymptote at 0. We also had another asymptote over here, which means that after that, the values don't really make sense. If you set that, I'll just write here real quick. Remember, this is the cost function. If you say 95, well, let's factor the v out. 95 minus v equals 0. Obviously, the v gives you 0, but this is another asymptote at 95 equals v. So after 95 miles an hour, the function sort of breaks down after that because there's an asymptote there. So it's basically a spike in cost that goes straight up to infinity. So after that, answers don't really make sense. So since this is to the right of the asymptote, we're going to throw that out and not use it. Okay. Let's move on to the next question. The rest of them are going to go pretty quickly since we did the hard work already. Since we're already 24 minutes into this video, that's a good thing. Let's see. So we have E. It says if L was increased to 500 miles, would the optimal speed increase, decrease, or stay the same? Okay, well, in other words, we go back to our equation here before we put in the numbers, and we'd say, okay, well, where do we put in L here? Well, we don't, because you guys remember up here somewhere, maybe on a previous page, we canceled out L. Okay, we divided it out of both sides. Let's see, it was right here. Okay, we canceled out L. So L doesn't really matter. L doesn't matter at all. So for E, when it says would it increase, decrease, or stay the same, it would stay the same because the length of the trip doesn't really matter. It could be 1,000,000 miles. You still need to go at the optimum speed to minimize your cost. Okay. What about if P was increased to $4.20 a gallon? Okay, what did we have in there before? We put 4 and instead put a 4.2 right there. Okay, well that's easy enough. Let's do that. So for just for this middle part, we get 95 plus 70 times 4.2 divided by 20. Okay, so that middle part would be 109.7, and we times that by -2, and we get -219. So 0.4. So it would change a little bit. Let's put this on a different piece of paper. So instead of having that function right there, which was our original function, we'd get v squared minus 219.4 v. Got to do the last one too. So I've got that inside, and this time I'm going to multiply by 95, and that would give me 10,421.5. 10,421.5 equals 0. Okay, so all I would have to do now is go into the calculator and change my numbers slightly. So 9, and then insert a 0.4, and then on this one, 10,421.5. Graph. Shouldn't change our graph very much at all. Should still show, yep, there they are. And we're just going to look at this one right here. We already know this one is going to be to the right of the asymptote. So intersection, go over here, and that should, yep, there it is, the little X mark, and it says 69.54. So V is equal to 69.54, and that's your velocity. So what happened? So let's go back and make sure that we understand what the question is asking. It says, if P was increased, would the optimal speed increase, decrease, or say the same? Well, it went from 69.9 to 69.54, so it decreased. Okay, so it took care of that. And then the last question, finally. So we have if W was decreased to 15. Okay, so likewise, let's go back up to here and put V squared minus 2V times 95 plus 70 times 4 over 15 this time, plus 95 times 95 plus 70 times 4 over 15. Okay, so we would need to type that in again. 95 times 70 times 4 divided by 15. Okay. And that number significantly changed, right? So if we multiplied that by -2, we would get, you see it there on the screen, V squared minus 3546.6 V. And let me make sure that, did I type that in correctly? Oh yeah, that's way too big. That seemed like it was way too big, but I didn't catch it at first. I put a times there instead of a plus, so let's fix that for sure. Can be much smaller than that. Yeah, there we go. There we go. Okay, so get rid of that, and then times that by -2, and you get, okay. Now let's write that down. V squared minus 227.33 V, and then let's see, times 95 would be plus 10,798.33 equals 0. Okay, so last little change here. So we go in here and we put 2 -227.3, and then 10,798.3. Graph. Calculate intersection point, enter, and we get that V is equal to 67.62. Okay, compared to 69.9, it went down to 67.2. So if you changed the what the driver earned per hour, then that cost would actually, or the velocity, optimum velocity would go down. It would also decrease. And that's it.